Today I'll be discussing about case insensitivity. I feel like it brings up a lot of battles. I was presenting my poster yesterday and everyone came up to me, the people at least who came up. They had very strong opinions about it. So let's see how it goes. So in this paper, we discuss mainly the pitfalls and the surprises that you get when you use and mix case sensitivities across different types of file systems. And before we get into it, a bit about me. As Peter already mentioned, I'm a final year PhD student, and I'm broadly interested in systems and file system and kernel security. So let's get started. The brief outline will be I'll discuss a bit about the background, the existing security work that has gone into these name-based attacks, talk about name collision, how it fits in, and then we'll go into the detection strategies, some evaluation, and then talk about certain defenses that we can employ. So with regards to file systems, typically they use names as handles to access a resource. So given a resource, you would typically have a name that associates or captures that specific resource that we want to talk about. You can think of it as a handle. Now, when we actually have a bad mapping between this name and this resource, we can run into data loss or corruption. You can accidentally overwrite an incorrect file. Or you can also leak confidential information. More profound attacks that exist in the security community also are there. So some of them are listed here. So they can be file squatting or link traversal attacks. I'll discuss more later on. But essentially, this name and resource mapping is kind of crucial in getting the security guarantees out of the file system. So putting this into broader perspective, we call the name-based attacks as name confusion attacks. And when you have this unexpected mapping, so what can happen is you can have aliases as one example. So in aliases, the same resource can have multiple names. So this can lead to, in case of symbolic links, it can lead to symbolic link traversal attacks. The other style of attack on this name resource mapping can be temporal in nature. So an attacker can come in and create the resource before the actual program code. And that will essentially give the attacker access to the resource that the program is writing to. And that's the classic squat attack. And prior academic research has mainly focused on these particular aspects. And we have extensive study to show why these are actually problems and how they can manifest. But one aspect about this collision business, especially with regards to file systems, has not really been studied well. And that's what this work focuses on. So to make it more concrete, with name collisions, what I mean is if you have two files, let's say small foo and big foo on a case-sensitive volume, and you want to move them over to a case-insensitive file system, only one of these can exist at a given time because only one of them can be actually addressed. You can either have the small foo or the capital foo, or you can do something sinister, and you can just have small foo with the contents of the other file and do vice versa. Or if the utility is smart enough, it can throw an error saying that, hey, what you are doing is wrong. If you look into the mappings between these ASCII foos, there is also this multilinguality that comes into picture. So all modern file systems will support different encoding that allows for different languages to be expressed. And so in case of ext4, for example, it supports Unicode. And you can have these various names that map to the same resource. And different file systems, however, have a different way to map these character sets. So something which is case insensitive on one file system can be case sensitive on another. So that also brings in new challenges. And through our results, we show that most of the utilities that we tested for are really not well behaved. And most of the time, that can also lead to security consequences. So before we start looking into the problem, this notion of case diversity is technically more prevalent and it's growing. Recently, with kernel 5.2, Linux kernel 5.2, ext4 added support for per directory case insensitivity. And in Linux on ext4 now, you can have folders which you can mark as case sensitive. And by default, they are sensitive. But you can mark folders as case insensitive. And so without even crossing the file system boundary, in the same mount point, you will have these variations in case. And different folders, so case-sensitive folders can contain insensitive folders can again contain case-sensitive folders, and so on and so forth. And the motivation from what I could make out from the mailing list is to support these kinds of applications. And also, historically, there have been other file systems that are supported on Linux which are case insensitive, namely something like FAT, GFS, ZFS, and so on and so forth. Also, recent patches have been proposed for a case insensitive tempfs. And we also have the WSL in which Windows actually embeds a small Linux kernel, and the Linux kernel has access to the Windows files as well as the Linux files itself. So it crosses case boundaries. Also, there are real-world implications with Git. The most recent CVE at 2021 was with regards to a collision between a symbolic link and a directory name, which eventually led to arbitrary script execution. This gets executed from Git hooks. I'll discuss it more later on. But there was another one in 2014 in which you could add the contents from the .git directory, which are not supposed to be added, technically not accessible from the command prompt. So it cannot be added to the version history. But if you used a different case, it could be added. And I believe Mercurial also suffers from this specific CVE. And so as you see, if programs are not careful and they make assumptions about the file system, you really can run into bad consequences. And that's what this paper is about. So to talk about our contributions, we coined this term name collisions and placed this in this hierarchy of other name collisions or name confusion style attacks and how it fits into the picture. We then go on to show unsafe responses can happen, and we develop a test suite or an automated testing strategy to test programs for these types of collisions that can happen. Then we demonstrate some novel exploits. And finally, we show that improper handling of case can actually lead to a variety of well-known security problems, but they only occur when you have collisions. So that's the necessary precondition. So now, if we go on to see, OK, how do we go and detect these collisions? Most obvious place to start looking is to look at the system call API, because that's the contract between the program and the kernel, or in this case, the file system. And so here, if you see, in the syscall trace, we have some file which is created at one point in time. Eventually, you create the capitalized, so you use that file, but this time you use a different name for accessing the same resource. And what we can say is, these inodes are, if the inodes match, we can say that the actual resource being accessed is the same, but the name is actually different. In this case, the name is different in terms of case. Now, if we look again back at the Git CVE, you see in the first line, you create a directory, which is capital A, and then eventually you create a symbolic link, again with a small a, which is a different case for capital A. Eventually, when it tries to use this file, Git thinks that the folder, the original capital A folder, still exists, and it tries to create this post-checkout script. But now what's ended up happening is it collides, this capital A is colliding with the name for symbolic A, the small a, and you end up with a symbolic link traversal. And this collision inside the file path leads to the final CVE from happening. So we argue that these create-use pairs are a succinct yet a good way to summarize what's going on in the process and to capture, meaningfully capture these collisions. Now, to identify these create-use pairs, one way we can use is strace, of course. But we can do better. We can actually look at audit-d, because audit-d also gives us the file system context. It will give us what paths were actually walked by the kernel to actually retrieve this specific resource. So example event looks like this. We are only interested in system call events, but a full system call event looks like this. If you dig a bit more into it, you'll see that it gives us some record type. What's the type of record? It gives us the path names like temp, temp root, what was accessed and traversed in the traversal. It gives us the inode and device identifiers, which we can use to uniquely pinpoint a file on the entire host machine. It gives us the system call, the executable. It also gives us the process ID. So we can essentially stitch this information together to extract these create-use pairs. And so we do the exact same thing. We wrote a tool, and you give it the raw audit-d logs. What it's going to present to you is a line or a pair of this format. that gives us the original audit context, the program, the system call, the unique identifier on the system, and the path with which it was accessed. So these create use pairs are what summarizes a process's accesses to the file system for us. And then we write a test suite to drive the various utilities to actually have collisions in them so that we can detect what kind of unsafe responses you get. So in this particular example, we assume that we will create a directory structure on a case-sensitive volume, and when we move it on the case-insensitive volume, we'll face collisions. In this particular case, the blue directories will collide, and the red files will collide. And so in our test suite, we generate all types of these various combinations between file types, directories, symbolic links, and then we use these as inputs to drive copying utilities, namely cp, tar, rsync. And so that's what we do. Now, once we do this, what are the results that we actually observe? So one is with respect to merging directories. So if you see in this example, the directories, the top-level directories, small dir and big dir will collide, and the file 2 is also going to collide. Most utilities are going to ignore one of the files. So one of the file 2s, in this case, will be just lost. It will have silent data loss. It will not even be reported. The other is, if the directory structures themselves have different permissions, incorrect metadata can get overlaid. So now file 1, which was originally inaccessible to everyone except for the owner, is now suddenly accessible to everyone else. And these utilities suffer from this, tar, zip, cp, rsync. Another one is in which you have a source directory. And in this case, if you see, there is a small dat, which is a symbolic link. Then there is a capital dat, which is a regular file. And when you transfer these over, you would first copy the symbolic link. And then CP, in a specific use case, will try to override this dat with the contents of capital dat. And it will end up with the symbolic link traversal, which will traverse and write outside the target directory. A more sinister kind of a use case was with rsync, in which we have double collision. In here, if you see, the top dirs both differ in case, and there is a parent directory that collides. And then you have two folders. One is a secret folder, which is a symbolic link. The other is an actual directory structure. Those names also collide. When you copy them over to a case-insensitive volume, the symbolic links ends up getting traversed because of the collision, and now you create this confidential file outside, and it can point to anywhere on the file system, so it's outside the target. It gets copied. And this specifically happens if you have a two-level collision, so your parent directories collide and the child collides. Only then this ends up happening for rsync. So that's a link traversal that happens. So how do we go about solving these problems? So if we only look at program defenses, well, they will be unreliable because we don't know as I previously mentioned, we don't know the rules that are used by the underlying file system to transfer cases or transform these cases. They are different for every file system and unique to them. A system-only defense will suffer from false positives because it doesn't know if you expect the collision or not. So a sound defense should include the program conveying, or the programmer in this case, conveying to the file system that, hey, in the previous examples, let's say I was copying from a case-sensitive source, so I do not expect collisions to happen. So that kind of intent needs to be conveyed down. Now, some ways we can do this is probably use the Open82 family of system calls and have a flag that, hey, I do not expect a collision. Make sure opens fail if you see a collision. Another way would be to canonicalize, add a system call that just returns a canonicalized path and a name. By canonicalized, I mean with the Unicode standard, you would normalize the path, and you would also fold the path and return that name. We can also go about adding system calls to query the underlying file system. Hey, are these two name strings the same or different? So that's another approach. So, well, that's me. This is the summary. It might help you ask questions. So you can feel free to reach me here, and you can look up the artifacts on this place. Thanks.